Good evening, every professors, ladies and gentlemen. I'm Pei-Chi from Building and Climate Laboratory of National Cheng University. I'm very honored to give this speech at the EMS Annual Meeting 2022 about my research, constructing wind corridor system as a mitigation strategy for the urban heat island effect in Taichung City. So before we start, I would like to express my gratitude to the co-author of this paper, Xinyu Ou, Zhouchang Zhang, and Ziping Lin. I will give this talk in several parts as shown on the slide. So let's start with the introduction. The intensity of urban heat island is a serious issue in Taiwan. One of the reasons is the poor ventilation and heat dissipation due to the density of building. Therefore, identify and construct urban wind corridor systems is the best way to improve the quality of living. This is an urban strategy that is being implemented in many cities around the world. In this paper, we would like to construct the hierarchy of wind corridor systems in Taichung City and to discuss the implementation of urban wind corridor systems at different scale of a city. According to the definition in the German National Guide, Environmental Meteorology, Climate and Air Pollution Maps for Cities and Regions, a ventilation lane is a preferred area for the transport of air near the ground due to direction, nature of the surface, and width. They are designed to facilitate the process of horizontal air exchange by means of low roughness lanes, straight or slightly curved, and relatively wide paths. In addition, the China Meteorological Administration had also released the Climate Feasibility Demonstration Standard, Urban Wind Corridor. It states that the principle for the designation of wind corridor is using geographic information technology to overlay background wind conditions, ventilate potential, breeze volume, urban heat island intensity, and spatial distribution of green spaces. They construct two kinds of wind corridor in urban area, which is called primary and secondary. Besides, a 2016 study by Xie et al. Used the Frontal Area Index (FAI) and the Lee Cost Path Analysis (LCP) to identify wind corridors. At the conclusion, they suggested that the connection of wind flow between water and greens should be considered in urban planning. Therefore, the steps of research process of this paper are shown in the figure, with three main steps. Step 1. Obtain information on the climatic characteristics of the city to facilitate the assessment of potential wind volume in the built-up area. Step 2. Set up ventilation principles and construct a wind corridor system. Finally, Step 3. Incorporate the wind corridor system into the urban plan and develop planning and design recommendations. We have distinguished wind corridors into two types, natural and urban wind corridors. A natural wind corridor is a specific wind flow from low to high temperature, created by natural differences in temperature and pressure, and shaped by topography. When the natural wind corridor enters the city and flows through areas of low wind resistance, the path can be called urban wind corridors. Urban wind corridors are further divided into two types, city-wide and local. A city-scale urban wind corridor is divided into primary and secondary wind corridors according to their ventilation capacity. If the scale of the study is zoomed to a partial area, the corridor is defined as a local corridor and may be called a Type 3 corridor. So below I will explain the designation of the urban wind corridor system step by step. The first step in creating an urban wind corridor is to define the prevailing summer wind in the area based on long-term wind speed and direction. In other words, the presence of a natural wind corridor allows the creation of an urban wind corridor. In general, the airflow during the daytime only enhances human thermal comfort slightly, while at night the temperature in the countryside drops significantly and cool air flow into the urban area facilitate urban heat exchange. Therefore, in this case, we have given priority to the summer nighttime wind direction while specifying the wind corridor system. Then, according to a combination of Landsat image recognition and cadastral data, we calculated the roughness length based on a suitable scale grid, as shown in the presentation on this page. After completing the calculations, we overlaid the visualization data with the geographical information layers. The paths can be mapped through the least cost path analysis and allow the wind to deflect in the bands when they encounter large areas of high roughness, over 2 meters in this case. To define the primary and secondary wind corridor, we calculate the number of high roughness length value grids that each route passes through. If a wind corridor flows along the rougher route, then it becomes weaker. The formula is shown in the page. Type 3 wind corridors are used to reduce the scale of study to a smaller block for the more specific implementation of the heat mitigation strategy. To identify the local urban wind corridors, the steps are the same as doing the citywide ones. The reference grid size was based on the study domain. At this scale, computational fluid dynamics (CFD) simulations were allowed to use to simulate the impact and variability of different cooling strategies on the environment. Using the microclimate measurements as input parameters, which enable us to confirm the effectiveness of the cooling strategy. Based on the methodology described above, we have identified several natural wind corridors for Taichung City as shown on the map. We choose the wind from the south during summer nights as the main wind direction for the urban wind corridor in Taichung City. The study area was defined as a 20 by 20 square kilometer in the area of city center. The result of the designation and construction are shown in the figure. Although it is estimated that the average wind speed of the Type 2 wind corridor is lower than that of the Type 1 wind corridor, since it has located in the core area of Taichung Heat Island, we believe that it has a high cooling benefit. In terms of the local scale, two methods and tools, namely the roughness length grid least cost path analysis and computational fluid dynamic simulation, were used to identify and compare the local urban wind corridor. The results were verified to have certain overlap rate. The result of the research above will facilitate more specific urban development regulations. For example, the volume of development and the standard of regulation, and so on. The study concludes that the advantage of the least cost path analysis of roughness length grid are that it is fast and has some accuracy. CFD simulation can also be used as an identification method for wind corridors, but it has proven to be relatively costly. It was also found that independently refining the grade of cells in the study area and referring to a more generalized grade of external area could improve the efficiency and accuracy of identifying type 3 wind corridors. However, there are still some drawbacks to the LCP analysis. For example, the single starting wind direction may limit the interpretation of the results due to the situation in the build-up area. The above is a brief description of this paper. I would like to thank the Urban Development Bahut of the Taichung City Government for this project. Thank you very much for the privilege of presenting this paper.